So where's the as a students could determine the order of reaction for a reactant. Uh, and that's just opportunity for skill development. In terms of order, we did all of that. Drawing to that tangents, etc. Initiate method. I guess they just need a very general overview of what the iodine clock reaction is. So I'll just explain. There are multiple reactions which could be considered iodine clock reactions. So this is what happens. Let me just Google the reaction. Just so I just want the one that's the more common one. Just 1 second. So my laptop just keeps hanging up. I'll probably be getting a new laptop uh this weekend. Just 1 second. This one. So what you can do is we can kind of go with this one. Uh that's the hydrogen peroxide variation. I just want a simple one. Just 1 second. The one that's involving. So I'll just give you an overview. So let's think of this one. Yep, this one. This is one example. So this is one example of what an iodine clock looks like. So basically, what happens is that remember what I told you about measuring rate of reaction. It's what you can do is you can measure rate by measuring any change that happens with respect to time, right? So you have a particular you've got a particular change, and that change could be anything. Now, one thing that you can do is you can keep the change fixed, right? And you can just measure the time. You can just like a 100-meter race. They don't measure the speed of the runners. What they just do is they just measure. They're just interested in 1 over time, right? So you keep the change fixed. You try and figure out like every reaction. You set a mark, and you try and figure out like what amount of time is needed for that change to happen. So you keep this change fixed, right? Now, and you just measure time. Now, in an iodine clock, what happens is this change is basically a color change, which basically happens like this. Okay, start. Okay, no, this is how it's going to happen. You're going to take a beaker, and in that beaker, you're going to add your reactants. Now, your reactants are you got three reactants, right? So you're going to add H2O2. You're going to add I minus 1, and you're going to add H plus 1. Okay, and that's the moment you add them together, that's when the reaction starts, right? Okay, Vardha, is this clear?
Yep, that's clear.
Okay, so you added these 3 reactions. And as a result, what will happen is that iodine gets produced. So I2 gets produced. Now, you're going to add starch to it. Do you know what starch, what color change happens when starch is added and iodine gets produced?
Is it from blue to brown? I don't know. I think I'm
It just becomes blue-black.
wrong.
I mean,
Oh
this
yeah,
is,
blue black.
it just becomes blue-black. So I think if I can, if this plays, my laptop is like really not working. Just a second. So if you can see, it's colorless right now, and then all of a sudden it turns blue-black, right? I don't know if you were able to see this, but it's going to be colorless, and then after a certain time, that's why it's called a clock, right? That after a certain time, like 10 seconds, 20 seconds, all of a sudden you start the reaction. Then after like 10, 20, 30, or whatever time it takes for the reaction to finish, then all of a sudden it abruptly turns blue-black. Okay?
Is that because there's a starch indicator inside?
Yes, there's a starch indicator, but we've got a problem here. That's when will the iodine get produced? The moment you add them, the moment you start the reaction, exactly at the same time iodine gets produced, right? I mean, is that clear that iodine is going to get produced in the first second, right?
Yep.
So that means the starch is going to go blue-black immediately, right? The moment you add these 3 things together, it's going to, so there's no clock at the moment, right? It's just that you add and all of a sudden it just goes blue-black, right? So there's no time interval. There's no it's t is equal to 0, right? Is that clear as well? Well, there's this
Yeah,
part.
that's clear.
Okay, so right now it's not working. It's not working as a clock, right? So what you do is you add this thiosulfate to it. I mean, this is thiosulfate. Now, what this thiosulfate does is that, let's say you add 10, 10 molecules of thiosulfate. So now what will happen is that the first 10 iodine that are going to get produced, the moment you start the reaction, the first 10 or 5, I mean, whatever the mole ratio is, so the initial amount of iodine is going to immediately, when it gets produced in the first reaction, it goes and reacts with the thiosulfate and it gets used up. So for the first few seconds, there is no iodine getting produced because all the iodine that's getting produced is reacting with the thiosulfate. So the starch is not going blue-black. Is that clear?
Could you please re-explain that?
I'm just saying that in the mixture, I mean, you had a problem, right? That the moment you add them up, iodine gets produced, starch goes blue-black. So right at the initial moment, starch goes blue-black, right? So there's no time interval that you're going to measure. So you add thiosulfate to the mixture. The purpose of adding thiosulfate to the solution is that the moment iodine gets produced, iodine goes and reacts with the thiosulfate, and that iodine gets converted into I minus 1. So the initial amounts of iodine that are getting produced immediately get used up. So if there's no initially iodine getting produced, why is it not getting produced? Because it's reacting with the thiosulfate, right? So you're not getting anything, right? So that means initially starch is not going blue-black. Is that clear?
But I thought it was the iodide ions that are produced.
In the first reaction, iodine gets produced. I mean,
Yep.
we're investigating the first reaction, right? So iodine gets produced and starch goes blue-black immediately, right? But now in the presence of thiosulfate, that iodine that gets produced, it goes on to react with the thiosulfate that's present in the mixture. So you've added some thiosulfate to it.
Okay.
And the purpose of adding the thiosulfate is that it will prevent the starch from going blue-black, because the initial amounts of iodine that are going to get produced are going to go and react with the thiosulfate, and they're going to turn into I-1. So starch does not react with I-1; it reacts with iodine. So initially, starch is not going to go blue-black. Okay, is that part clear?
Yep, it's clear.
But after a few seconds, the thiosulfate is going to get used up, and there's because it's going to react with the iodine. So it depends on how much you're adding, right? So let's say you added 10 moles of thiosulfate. So the initial 5 moles of iodine that are going to get produced according to the ratio are not going to do anything, because they're going to react with, they're not going to do anything with starch. They're going to go and react with the thiosulfate, and so nothing happens, right? But after the first 5 moles, all the thiosulfate has been used up. So now, if the first reaction produces any further iodine, then that iodine is going to go and react with starch, and it will go blue-black. Is this clear?
Yep.
So that's it. That's basically your stop. That's what you're going to time. So you're gonna add the same amount of thiosulfate so that the same amount of iodine initially gets used up. So if the whole thing happens quickly, so you're going to time the stopwatch when it turns blue-black, right? So that's your clock. Like after a certain time interval, the color of the solution is going to go blue-black. So your stopwatch is going to measure when the blue-black color appears. So if there's a higher concentration of H2O2 I-1 H+1, then the reaction would be fast. Iodine is going to get produced very quickly, and this reaction happens very quickly, and eventually the thiosulfate gets used up, and the iodine goes and reacts with the starch indicator, and everything happens very quickly. If the reaction is slow, it takes a longer time for the iodine to get produced and the starch to go blue-black. So you can always time when it's turning blue-black. Okay, so is this idea clear? What a iodine clock reaction is?
So is the iodine clock reaction the one where you do use the thiosulfate?
Yeah, that's why. I mean, because if you don't use the thiosulfate, it goes blue-black immediately, right?
Okay.
And it's like the reason it's like a clock is that it depends on how much thiosulfate you add. Like if you add 50 moles of thiosulfate, then it's going to go. It's going to take a much longer time for the starch to go blue-black. Okay,
Okay.
and that's about it. Now there's I think that's it. So that's all. In reaction kinetics, there's just one more thing, which is I think related to this graph, which is it's actually not mentioned over here. One second. So I think we're done with this chapter. We'll just do questions now. Just one second. Just a second, my laptop is stuck again. So let's start doing these questions. It finally opens. I said, now how would you calculate the rate of the reaction at 40 seconds? I mean, they've given you this reaction, and he's saying large excess of methanol is used. So that means if you use a large excess of methanol, so that would mean that methanol is effectively constant in the reaction because you're using a large excess of air. So we can say that methanol's concentration is basically constant. So they've plotted this chloroalkane. So how do you find rate at 40 seconds? What do you need to do? बढ़ता क्या होगा इसका?
Um,
I mean, they plotted concentration with respect to time. So what is rate?
so you would just divide it.
No, you're going to at 40 seconds, you're going to sketch a gradient. And let's say that's your gradient. Can you quickly tell me what the rate is by using this rough gradient? It's 0.015 divided by whatever this is. I think that's 90. So 0.015 mole per dm cube.
Is the time 90?
I think it's 90. It's approximately 90.
Okay. I got 1.67 times by 10 minus 4.
1.67?
Yep, times by 10 is power of minus 4.
T time 10 is per minus 4. Mole per dm cube per second, right? As the next one, use a graph to show that the overall reaction is first order. Explain. So how do you know that the overall reaction is first order?
So the concentration and rate have to change by the same factor.
See, that is first order. So, but how do you figure that out using this graph? I mean, there were three ways, right? One was that you knew the mechanism, right? You don't know the mechanism. The other one was that you could, uh, if they had done several experiments, but if they just plot the concentration with respect to time, there was a half-life method. The half-life method was that every time it takes for the concentration to decrease by what, half? So every time if it decreases by half, it's going to take the same time. So you can kind of estimate that the time is always exactly the same. Okay, so you got constant half-lives. Is that clear?
Yep.
In a second order reaction, the half-life would double. It would slow down a lot. And in a zero order reaction, the reaction would not slow down. So it's going to be a straight line, and the half-life, I mean, it's just going to be a straight line in that case. I say in a different reaction, which is also first order, 75% of the reactant is consumed in 320 seconds. Calculate the rate constant K for this reaction and state the units for K. As a first thing, can you figure out what the half-life is? And he's saying that it's a first order reaction. He's saying 75% of the reactant is consumed in 320 seconds. How many half-lives is this?
Is it 2?
Okay, so if I start off with 100%, right? Now in the first half-life, it's going to decrease to 50%. And then it's going to become half again. So the second half-life is that it's going to decrease to 25%. So 75% of in two half-lives, 75% of the reactant gets consumed. So that means this is 2 times, and it's a constant half-life in a first order reaction. So that's 320 seconds. That means one half-life is what? Is 180 seconds. Is that clear?
Isn't it 160?
Oh yeah,
I don't understand why it's 1.
It's 160.
Okay.
Because this one is 160. As the next one. Do you know what a homogeneous catalyst is?
Is it in the same phase as the reactants?
And heterogeneous is that it's going to be a different phase. That's definitely not in part of your. I'll do this one just to give you an idea how catalysts work, right? I mean, like in AS, we did study homogeneous heterogeneous catalysts, right? Why do you think this reaction is going to be slow? Like it's going to be extremely slow. Why? I mean, by just looking at this equation and look at the reactants, why do you think this reaction is going to be extremely slow? I mean, he's saying that it's slow. What's the reason for that?
Is it because they're ions?
And I mean, ions can react with each other. They're both negative ions, and negative ions they don't attract each other, so they repel each other, right? So so basically what a catalyst will do is, and this one is an example of a homogeneous catalyst. What a catalyst will do is that it will provide an alternate path, or it will take a completely different route as long as you get the same products. So these two, I mean, it's very hard to actually bring them together, right? They're both negatively charged. So what they do is they add Fe2 plus ions, for example, as catalysts, right? So when they add Fe2 plus, so when they so now when they add Fe2 plus, so when they add Fe2 plus, it goes and reacts with S2O8, 2 minus, turns it into 2SO4, 2 minus. 1 second, +2. So this is what's going on, that the iron ions, they start reacting with S28 and they turn it into SO42. So half the step is done by iron ions. Then the Fe3 plus comes back, and then it reacts separately with 2i minus 1, turns it into I2, they lose electrons, and Fe3 plus gets reduced back again, it turns into Fe2 plus again. Okay, so it's just an idea that although this is not in your course, it's just an idea that what happens in a homogeneous catalyst, that they provide alternate paths where if you look carefully, Fe2 plus remains unchanged. Fe2 plus goes and reacts separately with S28, turns it into SO4 minus 2. Then Fe3 plus comes along and reacts with I minus 1, turns it into I2. So you get both your products while the catalyst kind of remains unchanged. Okay? Is that clear? Do you understand what the alternative route concept is?
Yeah.
I saw this one. He's saying that there's a reaction going on. The reaction is second order with respect to nitrogen monoxide, and first order with respect to oxygen. So, and he's given you, under certain conditions, he's given you the value of the rate constant K as well, right? So you're being asked to construct a rate equation, which is what K is equal, that's K. NO squared, and O2 is 1. Now, can you figure out the rate of the reaction? You've got the rate equation, you've got the value of K as well. So they've given you some information over here. Can you find the rate of the reaction? If the concentration of NO is 7.2 times 10 power minus 5, oxygen is 1.9 times 10 power minus 3, and K is given over here. Can you try and calculate this?
Okay. I got 8.47 times by 10 to the power of minus 3.
And that's your rate. Because that's the rate for this one. As the next one is that he's saying that there's a rate equation given for this reaction. Water is not involved in the rate equation. That means if water is not written in the rate equation, that means water has what order?
0.
Okay, that's 0, and this is 1. The rate constant K is given under certain conditions. The reaction has a constant. Explain why this is. When you have a constant half-life, when the reaction has water order, that's first order, right?
Yep.
And use the information in the question to show that the half-life of this reaction is 2.77 times 10 power 4. Need that one we haven't done. Achha, so you're saying that 8 times. So calculate the time. You're given the half-life over here. Take this part. We're doing part 3. So we're given the half-life. He says that the starting concentration of this cisplatin is 8 times 10 power minus 6 moles are added to 100 cm cube. Calculate the time taken for the concentration to fall to this. So first thing, tell me what is the initial concentration, moles, and the volume is given. Try and calculate the initial concentration. What's the initial concentration?
8 times 10 to the power of minus 5.
Yes, the initial concentration is 8 times 10 power minus 5. So how many half-lives that the initial concentration decreases to 2.5 times 10 power minus 6? It's a first order reaction, so the half-life is constant. So how many half-lives is this?
I don't really understand how to work it out.
But you understand the question, right?
Yep.
So, I mean, this is 80 times 10 power minus 6, right? So we're starting at 80 and we want to decrease to what, 2.5? So first half-life, that's going to decrease it to what, 40? Second half-life, that decreases it to what, 20? Third
Why
half-life,
is it 80?
yeah, I just converted this into 80 times 10 power minus 6, right? So I'm just ignoring the 10 power minus 6. Is that clear?
Okay. Yeah.
So it's going to go from 80 to 40. And so basically I want 80 to decrease to 2.5, right? So it's going to go from 80 to 40, that's first half-life, 40 to 20, that's the second half-life, 20 to 10, that's the third half-life. Yeah, how many half-lives? This is the first, this is the second, this is the third. Then I want 10 to decrease to 5, so that's my fourth. And then 2.5, that's my fifth half-life. So the half-life is constant for first order reaction, so that's going to be multiplied by 5. Is this clear?
Yeah.
As the next one, we've got he's saying complete the rate equation, and the reaction is first order with respect to both. So the rate equation is K, both reactants NO power 1 and O3 power 1 as well. So both reactants. Can you try and calculate the unit initial rate and the unit as well? Both of them have the same concentration. And K is given over here.
I got 1.66 times by 10 to the power of minus 8.
And what are the units?
Is it mole dm minus 3 s minus 1?
Okay, that's the unit. Next one is the reaction is described in A2. A2, this one, is monitored over a period of time. Predict whether or not the graph of NO against time under these conditions show that the reaction has a constant half-life. Explain your answer. So they are monitoring the reaction. I mean, basically they're trying to plot the concentration time graph for this. So will it have constant half-life or will it not have constant half-life? They're plotting NO against time.
It will because it's a first order as a first order.
But it won't actually. I mean, it will actually because it's first order, but it won't because it can only be first order if the other variables are constant. And how do you keep
Oh,
the
okay.
other reactant concentrations constant by adding it in excess? But now both of them are added in equal amounts. So that means the reaction would actually be behaving as a second order reaction because the first order over here and the first order over here will combine. Because if this decreases, the reaction slows down, but this is decreasing simultaneously, so the reaction will also slow down. So it's going to be acting as a second order reaction. Okay, is that point clear?
Yeah, but could you please like write it down? Like, how would I explain that? I don't really understand how to explain it.
I mean, just the prediction is that prediction is obviously no, and the reasoning would be that uh, O3 is not in large excess. And it will affect rate of reaction. That's it. So it will affect rate, and I mean, it's just a 1 mark question. So you can further explain that. Hence, it will probably behave as a second order reaction because both the effects will get combined. As the next one, ठीक है, clear है?
Yeah, it's clear.
Now the next one is nitrogen oxide. You got at a high temperature, a small amount of platinum wire is added to a large amount of nitrous oxide. The reaction follows zero order kinetics. The platinum wire behaves as a catalyst. So sketch a graph of the axis below of reaction rate against time for the catalyzed decomposition of N2O under these conditions. So it's following zero order kinetics. How would the graph look like? How would the rate change with respect to time? What happens in zero order? Will the rate get affected when the reactants get used up?
No.
So that means it's just going to be constant, right? That's it. Okay, is this clear?
Yep.
So then sketch a graph on the axis below of N2 against time for this reaction. Now remember it says zero order kinetics, right? So how would the concentration of N2O decrease with respect to time? I mean, remember the rate is constant, right? So how would this graph look like? N2O is your reactant, it's getting used up.
Would it be like a slope downwards, like a straight line?
I think it's just going to be a straight line. It's not going to slow down, right? So basically we did the graphs thing. How big you have? Somewhere, no, this one. It's basically this one. Zero order kinetics, right? That was order one, that the concentration, it will slow down the reaction. And this is our zero order kinetics, right? As the next one is that's about heterogeneous. Describe the mode of action of a heterogeneous catalyst. We'll talk about that later. So just the reason we did this in AS. Heterogeneous catalyst has two modes. One is that it does adsorption. As it does adsorption, what it does is that the solid catalyst would break the reactant bonds. By adsorption, it will attract their electrons towards itself and it will form weak bonds. So the bonds between the strong bonds between the reactant molecules, they're going to break. Is that clear what adsorption is?
Yep, it's clear.
And then you have deadsorption because the catalyst does not form very strong bonds. So those bonds are going to break anyways, and eventually the atoms would be free to form new bonds. As I suggest, a reason why this reaction has zero order kinetics when the amount of nitrous oxide is large and the amount of platinum is small. So he's saying, why is it following zero order kinetics when a large amount of nitrous oxide is used? उसमें क्या होता है when you use a very large amount, the concentration of nitrous oxide pretty much remains constant, right? Is that clear?
Yep.
So if the concentration is basically not changing because you're adding you're using such a large amount, so that means even if it decreases a bit, a small amount, nothing happens to the speed of the reaction. ठीक है, ये clear है?
Yep.
चलो ठीक है, let's I'll send you this worksheet as well. Most of the questions are, I mean, we did most of the stuff in the notes. I'm just so I'll send you this one, okay? This one, these are more like latest questions, which are slightly more tricky. I mean, they're pretty much the same thing, but slightly more tricky, okay? So I'll send this worksheet
Okay.
as well. ठीक है, brother.
Okay, thank you.
Take care, Allah Hafiz.
Okay, you too. Allah Hafiz.